the FEFF code, and with apologies to those who like command line codes, I'm going to discuss this using our old Java graphical interface just for simplicity, because it makes it easy to discuss. So this presentation is joint. It was done largely by Josh Cass, who's now the senior developer of the FEFF code, and Fernando Villa. And it was developed at University of Washington for many years, but it's now going to move to Stanford beginning in the end of this year, which will be a permanent home. It's part of the Theory Institute at Stanford. Let's see, I can go forward, can't I? Okay. So first of all, there's the installation. So hopefully that should be automatic, unless you have a Macintosh, in which case you have to get the right version of Java or it complains. But assuming that you do that, then the first step is to run the installer and put it in some nice place like program files. The executables are all there, and once you get it, you should be able to run the code, and maybe you can follow along with me. This is not, there we go. All right, so you should finally get a screen that has this Java GUI on here. Okay, well, this is a kind of preview of what we're going to discuss. So basically, I'll discuss the structure of the code itself and the sequence of steps. We call them modules. The input that's needed to run it, it'll be structural and other inputs. How to get the muffin tin potentials, and where to get the input files. You can make them yourself, but they're available online very many places, and it's useful to get structures from various places. What the output looks like, what kind of print options are available, and then various practical considerations. Okay, well, the main FEFF website is feffproject.org, but the code is now living on GitHub, and it's a common password for everyone right now, subject to change. Okay?
It has nothing to do with Windows 10, does it?
No, it has to do with FEFF 10. No, we have no allegiance to this company across the... okay, but anyway, we do, like other codes, we have versions for executables for Windows, Mac, Linux, and hopefully something will work for you.
Would you be able to turn on the mic?
I'm not muted.
In the gym, I think.
Oh, sorry.
Maybe like that, because the mic is off.
Can you hear us now? Hello? Let's find out.
How about now? Is it okay? Shall I
Yes,
continue?
okay, it works now.
Okay. All right, thank you. Okay. But now this doesn't work. So you can either have the microphone or you can have...
No, we have to go on the.
Okay.
Does it work?
Yes, works fine. Okay. Okay, so a Fortran compiler is optional only if you want to run it on your own mainframe and do it in MPI, which I recommend because if you have a lot of cores, you can run it much faster. Okay, we've changed the installer. This was the old installer. There's a new one. You probably noticed. Doesn't matter. And what I want to mention is that there are various examples. And depending on the operating system, it will either be in a file called JFEFF examples or FEFF10 examples. If you can't find one, hopefully you'll find the other. But it's exactly the same, but I think the formats are a little different depending on the operating system. Okay, so this is what you want to get to, and you find this graphical interface, which basically has all the defaults and input variables that one needs to run a calculation. I'm doing copper. Copper is our guinea pig. Where is this? And we do have a little JMOL viewer, so you can see the structure and move it around. Unfortunately, I don't have that. But with your mouse, does anybody have the JFEF actually on there? Oh, okay. Yeah, so you can move it to show the rest of the. So it may be useful if you actually have the GUI running. How many people have the GUI running now? Oh, a few. Okay. So maybe just follow along with me and show who's ever beside you what's going on. So briefly, these are this is the structure. FEFF is a cluster code. It's done in real space. There's no periodicity used. Actually, there is a K-space module that runs CIF files, but the calculations are done in real space usually. And typically, about 100, 150 atoms are needed to get good convergence in Zanes. So this is what we have. The fast calculation that I'm doing here, this is one of our standard samples, is done for XFs, and it's done on this L2 edge. It would also produce for you the local densities of states, S, P, D, and F, so you can compare with other codes if you want. And I think what you can do is go to the file, and I may be getting ahead of myself. Well, this is already open. If you open an example, you don't have to do it. It already is loaded. So all we can do, I would comment out the LDOS for starters, because we don't need it. Let's just do a fast spectroscopy run to see if we like it. So save and run. And we can see which machine runs faster. Here we go, calculating XF spectra. Finished. So,
First,
who's next? Raise your hand when your calculation's done. Okay, it's 2, 3, 4, 5. Okay. Well, let's follow along the lecture that was prepared by Josh and Fernando, because I'm probably getting ahead of myself, but this will just give you an idea of how it works. It's really, this is meant to be a sanity test to make sure your computer works and it produces the same calculation that my machine did. So let's go ahead. We'll do 2 quick tests, the copper for a kind of a cluster FCC structure, and then an example molecule to make sure that it's working. Okay, so let's go back and do the test. Well, we did copper, but to make sure it's working, what you want to do now is to go down to this button that says plot and push the button. Okay? So, voila. Okay, so that's the L2 edge of copper. But now you want to see whether it works or not. Everybody get the plot? Okay, that's what your machine did. Now if you go up to File at the top left or of the plot, you'll see Open. Press Open and scroll to the right till you see something called Reference Data. And open it. Okay, so now we have 2 plots on top of each other. And if you click on one of those, if you don't like the color, you can change it to green. But hopefully they're on top of each other. And to see whether they are, you can home in on this. This is a dynamic plot tool. You can zoom in on any region of the spectrum you want. And boy, I can't tell the difference. They're really on top. And by clicking on the color, you can switch from the reference data to your data. So did anybody find any discrepancy? Any at all? None? Is it sort of right on top of each other? Yeah, okay, so that's good. So
these reference data are data
that were
prepared before.
prepared before with the same input on our machine. So, okay, so any questions?
Yes, is there a command line easy way to plot the thing?
Is there what?
A command line instead of the graphical interface to plot the things?
What do you mean comment?
No, command line because I don't have the Java interface here.
Oh, you mean with if you do have GNU plot, you can go to the output xmu.dat and then plot it with GNU plot.
Oh, okay.
And you want to plot columns 1 and 4. They're listed down here. You can see what's listed. It gives you the file name and the file, which is xfs .dat, and then it's columns 1 and 4. Okay, 1 is the photon energy, 2 is the photoelectron energy relative to the edge. 3 is 3 is K, square root of energy minus the chemical potential. So that's the effective photoelectron momentum. 4 is the X-ray absorption. 5 is the background and 6 is the fine structure. Okay, so let's do this next example. So we go to File, and let's do Open Example. And we're going to do Zanes. Click on Zanes. We're going to do GeCl4, 5 atoms. So that should do that in about a microsecond. Open it. Okay, and if you do that, you should see that now it fills in all the fields for this molecule. Okay, raise your hand if it did that properly, or if you're able to do that. So one person, 2, 3. Okay, so now let's view it and make sure we're doing GeCl4. All right, looks like GeCl4. I think it's color-coded. Okay, save and run. Okay, launching FEFF. Okay. So now it's doing Zane, so it has to do a few hundred points. It's doing one thread, calculating the spectra. Okay, I'm finished. Finished? Okay. All right. Okay, now if we go to plot again. Okay, so this is the spectrum of GeCl4 with the muffin tin approximation, ASA. I realize it's not full potential, but it's not too horrible. And let's compare the reference data just to make sure that it works.
Please check the discussion if somebody has written something.
What?
Somebody has written something.
Okay, anyway, so you can check these and change the color. This is in purple. We'll change it to red. All right, well, it's basically on top of each other. It's strange that you might have problems, but you can believe everything is okay.
Points. Can you make it into points?
Not only the curve, but their point.
Oh, into points? Probably. If you zero in on it, actually, I'm not sure.
Okay.
You can do everything with computers, but I don't know what style of the lines they managed to use.
Very important question. How can I export data set?
How can you what?
Export.
Oh, you export. Actually, from JFEF, it's a little difficult, but you have to go to one of the program files. If you open up that directory where this is located, it'll be a GeCl4 directory. You'll see a file called xmu.dat. It's XMU because if you use mu, it's an integer, you know. So we put an X. Anyway,
And that is the XML.
that's where the data is. Yeah, you can export any of these files by going to the directory. Each of the examples is done in a separate directory, and all the data is there. Okay, was there any question from the...
No, they were just a bit confused why nothing is changing.
Oh. Okay, now things are changing. This was a recap of the formalism. So what we did was, for the GeCl4, we did this matrix inverse and repeated it over a grid of about 100 energy points. This is the flow diagram to see how it works. As you can imagine, you take the input, create a density. We start with an overlapped atom construction of the density. We overlap them by a factor of 1.3 and get our starting point ASA, and then we do a self-consistent loop until the chemical potential is converged to millirydberg accuracy or better. Once we have that all converged, we calculate the potentials, then get some radial matrix elements and screening and scattering phase shifts, and then either do the full multiple scattering or the path expansion. Once we have that, we construct the spectrum, and then we put in Debye-Waller factors. So for the multiple scattering path expansion, each path has a given length, and we do a Debye model by fluctuating the total distance along that path. So each path has its own Debye-Waller factor. You have to specify the Debye temperature and the temperature in order to do that, which will be on the GUI, but I'll come to that later. For full multiple scattering, what we do is we do we take G of R and R prime, one of those path legs, and we average that over the distances R minus R prime. And that's actually a pretty good approximation, including atom-atom correlations for the multiple scattering, the vibrational effect on the Zanes. It agrees exactly at the single scattering level, and that's the dominant contribution. Anyway, that's how we do it. Please interrupt me if you have questions as we go along. Okay, anyway, it's all sort of automated in terms of these modules. The modules are basically code modules which we have linked together automatically so that the output of one is used as input of the other. And as I said, first we read the input. This is an input parser. It's free format, anything you want, no format whatsoever. Doesn't matter what order, the parser will figure it out. And okay, so here's a self-consistent. They're all kind of obvious if you look at the names. Full multiple scattering, right? Make the trace over Green's function, all right? So path expansion, and then FF2X means the FEFF algorithm to X, X meaning some X-ray spectrum, whatever it is. So depending on the arguments, it'll produce a different result. This SFconf is our spectral function convolution. That takes extra work, so it's fine to leave that off. Keep the default. The default, I think, is 0.9. And if you're doing XFs, that's probably okay. It's mostly a constant, but you can put it in if you want. And then you can do various other spectra, Compton, Eels. There's a whole suite of spectra that you can calculate from the examples. Okay, well, we're back to JFEF example 2, which is boron nitride, although it says copper here, I don't know why. It's supposed to say boron nitride. I don't know if you want to take the time to do this, because it takes a little longer, but I suppose we could. You can always kill it if it takes too long and you don't want to wait around. So shall we do it, just for the heck of it? Oops. I think that's Zane's. BN Crystal, how about that? Open Sesame. Okay, there we go. And I'm going to turn off the LDOS actually. Save and run. All right, off it goes. So this may take a little longer, but we'll just see. Some of these modern laptops are really great. But meanwhile, I'll keep talking.
In this example, you have click both FMS and pass expansion. Is that not a contradiction? Shouldn't you make a choice between one of the two?
That's actually, okay. It looks like it's a contradiction, but in the end, you see it says XFs or Zanes, and for XFs, it will ignore that FMS and it'll run the path expansion. Yeah, that's right. So it may be a little misleading. How are we doing here? Oh, done. Hey. Okay. Anybody else?
Yes.
Okay. So I guess we should check it out. Well, you guys can check it out and let me know if they agree. Looks good? Okay. So it's pretty fast, actually. I mean, it's not as good as some full potential codes, but it gives you a good idea of what to expect, and you can get local densities of states, etc. So it's good if you want to get an idea of what some new material looks like. It's a good starting point. Okay, continuing. Okay, so we loaded this, and then you can look at the various features. And by the way, if you go to the graphical interface and take your mouse and hover it over in the Zanes, the 4.0, where you'll see that it tells you what that variable is. And it turns out to be the maximum value of the momentum in Zanes, which is now k equals 4. And this is in Angstrom's inverse. So that's about 2. If you take it in half, it's 2 atomic units. And 2 squared is 4 Rydberg. So this goes out to about 60 volts in the calculations. And you can hover over the next port, which is the step, gives you what the grid is, and so on and so forth. So you can play with the grids and all of these things. If you go down to exchange, you can see that we have Hedin-Lundquist, or Dirac-Hara, or ground state, which means nothing, or partly non-local. And if you look at the core hole, it gives you some options too. The final state rule is the default. That's a real just self-consistent DFT screening. Or there's an RPA, or there's nothing if you don't want a core hole in the calculation. It's interesting. For L-shell metals, as Hubert knows, you turn the core hole off, right? Yeah, nobody knows why. Or at least I don't really know why. It appears to be very strongly screened, so you get better results without a core hole. Actually, you really need to do a beta saltpeter or a better calculation on that. Okay. Okay, so we ran the BN example. Okay, so if you're using command line, then you have to actually look at the input file. Oh, by the way, can you tell me how much time I have?
You have about 8 minutes.
8 minutes.
Yeah.
Okay, so I'll move fast then. Okay, so first of all, this is the input file, and as I said, the input parser doesn't care which order you do things in. So you give it a title, whatever you want. You can specify an edge. Zane's calculation, this is one of the spectroscopies. It could be Compton or it could be XAFs. If you want local densities of states, you give it a minimum, a maximum, and a step. The control is whether or not to run these modules. This is with all of them run. But if you're doing fitting, you might want to just run the last one and keep only changing the fit. So you don't have to rerun the code each time if you're doing fits. And some software like Athena or other packages basically just play with spectra. They keep the potentials the same and just calculate the last card. Okay, this is a radius for the self-consistent calculation. For the self-consistent convergence, you only need about 50 atoms. Somehow you don't need the whole cluster because going out to 150 doesn't really change the densities that much. For the full multiple scattering, though, you go to a bigger cluster. This is typically 150 atoms. Okay, the potentials in this boron nitride example, you identify the potentials by an index, a potential index. 0 is always where the core hole is supposed to be. So you would either put the 0 on the boron, if you want a boron K shell or L shell, or you would put it on the nitrogen. Here we put it on the boron. So you're getting boron, say K shell or L shell or whatever. These are the maximum angular momenta that we use in the calculations. And that's typically L plus 1 of the kind of valence angular momentum. So you can kind of guess that. And then there's X, Y, Z coordinates of the atoms in this boron nitride.
Sorry, what is the difference between the two of the
This one?
Yeah, the first one and the second.
One's for the muffin tin, self-consistent muffin tin calculation for the SCF, and the other's for the full multiple scattering calculation. So it's two different modules running. One just to get the potentials, and then the other for full multiple scattering, you might have to go up to 4 or 5. Like this for the self-consistent calculation, you can get away with a very small L because you're just calculating over a few volts over the valence band. But for full multiple scattering, this L max has to be of the order of K max squared. So, or sorry, order of K max. K max A is L max, where A is sort of the muffin tin radius.
John, what is the meaning of stoichiometry here?
Okay, stoichiometry, this code is a little bit intelligent. Stoichiometry forces the charge counts on the boron and the nitrogen muffin tin spheres to be 1-to-1. Okay, so there will be a little bit of charge transfer in the self-consistent calculation, but you can impose stoichiometry, like if you have a nice crystal, and that'll give you stable potentials. Okay, so it did the whole run if you have all those control things set to 1 or you have all those boxes checked. Okay, and as I said, if you want the high end, then we need to run it in MPI. Okay. Okay, so I think I've said this before. These are the modules that are run, and the print statement allows you to print various things. You can print potentials, you can print spectra. Often you don't want to print that stuff, or you don't really need it, but you can print phase shifts, you can print XFs. And I gave you a link to the manual where all those particular output files are discussed. So xmu.dat is a nice file to know. That has the spectra, it has potential, it has everything. that you really need on spectroscopy. So you say I only have 3 minutes now, right?
Something like it.
Okay. All right. These are the various properties. Edge, LDOS, X-ray emission, so on and so forth. I'm going to speed up now. Core hole type, I think we've mentioned all this before. This is to add vibrations. You need a temperature and a Debye temperature. So if you click on that, you get all those things. If you have a molecule, just put 1 in there. And otherwise, it's the number of atoms of a given type in a unit cell. XYZ, this index of the potential is sort of obvious, and it gives you a distance. And distances are in angstroms. So we use electron volts and angstroms for dimensions. Okay. Going quickly through the details, as I said before, the main parts are the choice of model from the file, and then we go to the spectrum settings, XFs, and what the edge is and the ranges. That's the run. These are the various options. We'll go through them quickly. Okay. Anyway, where to get the info to build an input file. So there's this collection called Web Atoms, which is at Argonne, produced by Matt Newville and Bruce Ravel. There's the Materials Project. There's now a massive amount of FEFF input files at the Materials Project, if you have a solid. So sorry about the molecules. But they've done 500,000 materials there, and they have the K-edge calculated with FEFF, and they supplied the input file. But you can get others at this crystallographic database. Okay, what happened? Sorry. Okay, output files. So these are the various files. The XMU is the spectrum. The log file gives you the output. It tells you about errors, if there are any, or what it's doing. The LDOS NN.dat is the local density of states, SPDF, for each potential. So it's a local density of states on each atom or on the core hole. And then the potentials, if you want it. Okay, so SCF, as I said, always starts small. FMS radius, I start with 150 atoms. I don't start small. Because it doesn't take that much longer. That's what you need. And what do they say? Too few. I don't know what that means. What it says is you have to at least have unique potentials for each unique atom. So don't use a lot of those. Mostly, every atom, every boron's more or less the same. But sometimes you have 2 different types of atom in a unit cell. Like you'll have one in an open structure and one in not. So you give them different potential indices. Okay, parallel FEFF, you'll love it. And finally, there's Corvus, which I don't have time to discuss, but that's our intelligent workflow generator for advanced spectroscopies, where we couple multiple codes. Showed that before. So this is the summary. And it says be ready for the practicum session, but you've already done the practicum session. We've done both at the same time. Okay, I'm going to stop. Thank you very much.
We have about 5 minutes for questions.
Yes, yes, John. With the huge database of FEFF spectra that have you started to build a machine learning algorithm to deal with the to use this data?
Actually, of course, other people have beat us to the punch. Anatoly Frankel has done this. If you look up Frankel, AI Frankel, Brookhaven, you'll see they have a couple machine learning papers. They were looking for enhanced catalysts. At the Materials Project, there is a machine learning project. At Toyota Research, if you look up Linda Hung, Toyota Research, they're using this database to design new materials for Toyota cars.
You mean the FEFF database?
Yes. Using the Materials Project. Yeah. And fast throughput, yeah, with FEFF. So the answer is yes, being done.
Great.
Any more questions?
Just you mentioned for the potential screening. What do you mean by screening of the potential?
Core hole potential?
Core hole potential.
Okay, you start with the bare core hole, Z1. Okay, but then if you turn it on self-consistently, the charge will relax and electrons will move in. So the effective core hole potential will be something like a half.
So
And it'll have a different.
So the screening was meant for core hole?
Yes.
Okay.
Yes, yeah. It's core hole screening. And it can be RPA or DFT or nothing. That's what we have now.
Anything else, anyone? It's your last chance to ask John something.
I'm not going to be here next week. But it's not your last chance. Actually, I do carry my phone around and look at email since I don't have anything else to do.
Okay, then it's perfect timing. Thank you very much.
Okay. And thank you. Really, it was a pleasure meeting all of you this week. This was, for me, my pleasure.
And now we have about 20 minutes for technical details of the next week.
Really?